Hi class, Philippe Fulsac here for Stat 2450, and in this video what I will want to do is show you a few exercises with their solution, and they are related to the material I have presented in the second lecture of module 2, so M2L2. So consider this as a video that will help you for example, your assignment. Okay? So I will cover several topics. First, I will show you how to manipulate the probability mass function and or probability density function of a distribution. Okay, so we'll see how to we can use this in R. Okay, for the normal distribution or maybe for the binomial distribution. So I would use the binomial distribution as an example of discrete distribution and the normal distribution as an example of continuous distribution. Okay, so we'll do that. We'll also look at CDF, the cumulative distribution function. Okay, so that will be the first topic. The second topic, I am going to show you, well, to talk about a special, very important law in statistics, which is the law of a large number. Okay, and this is very important. It is an extremely important law in probability and in statistics. In fact, when you talk about a law here, we should rather talk about a theorem. So it is actually a result that you can prove. Okay, it is I mean, it is usual to refer to it as a law. Okay, maybe because that was a word that was used a long time ago, maybe 2 centuries ago, when this law when this result was discovered. And I'll talk about that law of large number, and I will use animation in R to actually give you a pretty rendering of this theorem, graphic rendering, okay, of this theorem. And third, um, what I will do is I will actually talk a little bit about Markov chains. Okay, that's kind of a practical application of what we do in lecture 2. Okay, so let's start without further ado with the first topic: PMF, PDF, CDF. Okay, so let's consider, for example, a binomial distribution with size 4 and parameter, a probability parameter 1/4. What does it mean? So that, okay, this distribution represents basically the number of successes that you observe in 4 trials, each trial being independent and each trial having a probability of 1/4. Okay, so in each trial we have a probability success of or success probability of 1/4, which means that if we consider our 4 trials as 0 and 1s, failure, success, success, failure, okay? So here we would have 2 success and the output of your random variable would be 2, okay? Because that's the number of successes. And that's what you observe, okay? So we don't actually observe the left-hand side here. We observe directly the 2, okay? So if we do another draw, maybe you would observe 0 success, okay? That can happen only in this way. So the probability that we have 0 success, of course, is less than the probability of having 2 successes, okay? Because there are more ways to realize 2s, okay? In fact, you can realize 2s in many ways, okay? I show you a few ways, or show a few examples, okay? And so on, okay? But you can only realize 0 successes here, like this. Vice versa, if you want to, the maximum value of success that you can have is this, and there's also only one possibility for that, okay? So again, we don't observe the left side here, but we observe the right side, okay? For number of successes. So here, this is the observed value of the binomial random variable. Okay, and of course, a binomial of size 4 is equivalent to the sum of 4 independent Bernoulli random variables, each with the same probability of success. Okay, so this is really the same as the probability, same as probability of the sum of 3 Bernoullis. Okay, B1 plus B2 plus B3 plus B4. Okay, and I say 4 because here I'm using a size of 4. Okay, so suppose you want to do some simulation. Okay, well, we have a size of 4. Traditionally, we use big N for the size. The probability of success here turns out to be 1 divided by 4. Okay, so that's just 1 divided by N. And if I want to generate 100 samples from the binomial, I can say that in XO, observed value of my observation, that's my data, and I call a random binom to generate this. I need to provide the number of samples, N, 100 here, the size, and the probability parameter. That's it. And of course, each time I run this, I get a different set of value. Of course, it's random, right? And you can see that, well, you have zeros, you have ones, you have twos, you have threes, and do we have any four? We'll see. Okay, we don't have a 4. Okay, so occasionally, okay, we don't have 4s. So I'm going to take one. You're going to see why later. I'm going to take well, an example where 4 appears in the list of values. Okay, and again, this depends, totally depends. It's random. Okay, so sometimes 4 will appear. Actually, I have enough samples here to have 4 appearing in many cases. Okay, so well, here again I don't have 4, and here I have a 4. Okay, so that's it. So let's say I use this data. So now I have my table here, and what does this table represent? Well, it just counts the frequencies. Okay, meaning 23 is a number of zeros in this array. Okay, so I got 23 zeros, 53 ones, 17 twos, and so on. Okay, so this is what you can call the well, the table of absolute counts in 100 trials. Okay, and that's what we observe. So here, this is a table. We can see the values. So 0 appears 23 times, 1 appears 53 times, and so on. But that's a complex object. Okay, it has a name and set of values, set of frequencies. If I just want to extract the frequencies and treat them as a number, I can use FO. So I'm going to call them frequency observed. Okay, and that I'm just applying as numeric to convert this table to numeric, and then only that part will be kept, and you will see only the bottom part. Okay, now I have my observed frequencies. So in 100 trials, that's what I got. I got 23 zeros, okay, from my observation of zeros, 53 observations of ones, and so on. Now I want to compare to theory. Okay, so how many successes do we expect to have in n trials if the probability of success is 1 per trial? Well, clearly, okay, we expect to have n times p successes. Okay, so for the p's, okay, what I'm going to do is I'm going to actually I am going to apply now the probability mass function of the binomial, and I'm going to apply that to 0, to 1, to 2, to 3, and to n. And this way, I will get the values, the probability of getting 0. Now this is theory, okay? Theoretical probability of getting 0. Theoretical probability, according to the binomial, of getting a 1, of getting a 2, a 3, and a 4. You can see that the mode of the distribution, which is the value of the random variable that maximizes the probability, the mode is 2. Okay, 2 is the most likely outcome. 1 is slightly less likely, 3 even less, and so on. Okay, and 4 is the smallest probability, the value that has the smallest probability. Okay, so this is why sometimes we will not see this 4. Okay. Okay, so now we have probabilities of each event, probability of 0, probability of 1, so I can actually I could write this as a table actually. Okay, so basically you have these probabilities here. Okay, so probability of getting 0, probability of getting 1, probability of getting 2. So this is called probability of getting 3 and probability of getting 4. These are probabilities, okay? So this is called the probability mass function, okay? You have the values of your discrete random variable, 0, 1, 2, 3, 4. These are the possible outcome of your binomial random variable of size 4. And for each value, you have a probability. Now, in 100 trials, okay, I would expect 100 times this, okay. So, in other words, I expect to have 31.6 values of zeros, 42. So this doesn't have to be exact, of course. Okay, it's because it's not necessarily an integer. Okay, but that's my expected according to probability in 100 trials. This is how many zeros I should expect to see, how many ones I should expect to see, and so on. Okay, so I call this the theoretical frequencies, FT, frequency theoretical. And so now I've calculated, I have my theoretical frequencies and my observed frequencies, okay? So maybe what I can do is I can compare them, or I can plot the theoretical frequencies. So here are my theoretical frequencies in 100 trials again, okay? So I can say main equal, so I can give a title to the plot, okay? Frequencies, um, theoretical frequencies, 400 trials. Theoretical, okay? Frequencies, 400, 400 trials, samples of binomial, okay? Of size 4 and probability 0.25. Okay, no, so that's my title. A bit of a long title here, and that's it. Okay, 0 should appear a bit above 30 times, 1 should appear a bit over 40 times, 2 around 20 times, and so on. Okay, all right. So and I can either look at if I want to round or get the floor of the theoretical frequencies, I can display them as integer. Okay, so now what I can do is I can generate a table to compare the observed frequencies and the model of theoretical frequencies. So what I do is I take my two arrays of frequencies, observed and theoretical. I take this, I combine them. I make a matrix with 5 columns. Why 5 columns? Because I have either 0 or 1 or 2 or 3 or 5 successes. 5 columns because this is the length of each vector. And so now I feed that by row, okay? I feed my data by row because I'm feeding first this and then second that. But because the theoretical frequencies are actually not rounded, okay, everything will be converted to real numbers. Okay, so here I will have real numbers. So I can give a name to the columns. So the columns are going to be called 0, 1, 2, 3, 4 because I have either 0 success or 1 or 2 or 3 or 4. I can give a name to the rows of this matrix, row names of data. I say observed because the first the first row is for observed frequencies, and the second row is for model frequencies. Okay, so my second name is model, And now I can create a new object, which is I reformat my matrix as a table, and I show this as I showed my table. And here we are, okay? I have a nice comparison of my observed, okay, or empirical frequencies and my theoretical frequencies. And you can see that they are quite close, okay? In fact, they should converge. These frequencies will converge to each other, and that's a consequence of the law of large number, which we'll see later. Okay, we'll do an experiment in which we actually do a convergence experiment to show that indeed, when I increase sample size precisely, the theoretical frequencies converge to with probability 1 to the observed frequencies. If you are not happy with all these trailing zeros here and you find that table a bit confusing, you can simplify it a little bit by turning the frequencies to integers. Okay, that's what I did here, and then you get a simpler version. Okay, of a simpler version of the table. Okay. All right. So let's now talk about probability density function. So I use, just to show you how this can be used, suppose I'm interested in the normal distribution and I want to calculate the probability density function, okay, of the normal distribution at 2, okay, at x equal 2. So I want to calculate basically f of x, where f is a PDF of the normal, okay, and well, here, okay, I need to use D because it's a PDF, and I need to use norm for the normal. So the least you can do is to provide a value here, x equal 2, but be careful, this is minimalist programming, but this is not complete because this assumes, okay, that I'm using a standard normal distribution with mean 0 and variance 1. So if you want to actually provide the mean and the standard deviation, you need to say mean equals 0 and standard deviation equal 1. So the two methods are equivalent. Okay. For the standard normal distribution, for these parameters, because they are the default parameter, you don't need to provide them. Okay, so let's go. Okay, and now what we can do is we can draw the PDF. Okay, and how do I do that? I create a sequence of numbers between -4 and 4, regularly spaced by 0.01. I apply the denorm function to, so again, taking n01 to x, to the grid of value, and I plot the value. Then I draw a vertical line, v, at the value 2, okay? And I get that. I can actually draw a vertical line in the middle, 0 at 0, say, okay? If I want to do a more interesting plot, I can do this. I can use the polygon function, okay? And here, what I do is I fill between a value and another. So I decide to fill here between -1 and 1, okay? That's my choice. So and I build a polygon of points, okay? That surrounds the area I want to color, and I fill the polygon. So I give all the x values of the polygon, I give all the y values of the polygon, okay, and I provide the color of the polygon, okay, and I get that plot, okay. So pretty straightforward to use polygons and to draw anything you want as in color in R, okay. Okay, you will see later that there is a simple way to actually achieve this. It is not as general. This is pretty general. Okay, it means that you can draw anything now. Okay, with the polygon function. So you can draw a square, you can draw a star, you can draw any like a tiger. You can go draw a bird. You can draw yourself if you want. Okay, using polygons. Okay as long as you have the points around the polygon. So the points are, you must actually use polygons around this. So I create my points here along the normal, the density curve. Then I descend here to the x-axis. I create another point here, and I go back. Okay, that's how I create my x and y values. Okay. Okay. So now let's go to and to see how we can use cumulative distribution functions and quantiles. By definition, the cumulative CDF function is of at the value of the CDF function at x is a probability that x is less than little x. Okay, the quantile function is the reverse, the reciprocal of that function. Okay, so suppose you want to calculate that quantity, okay, and you know the distribution of x. Let's say that the distribution is a normal. So what is the probability that -1 is less than x and less than 3? Okay. What's the probability that a random variable distributed as a normal with mean 2 and standard deviation 5 um, uh, is between or belongs to interval -1, 3? What you do is you calculate the CDF at the upper bound of the interval, and you remove the value of the CDF at the lower bound. Okay, and that's how you can calculate this. Here you can check that I'm only doing the same plot again, but with now these values. Okay, so -1, 3, and I color this area. Okay, so what is this area here? This area is 0.3. Okay, so there's a probability of 30% of being between -1 and 3 for normal with mean 2 and standard deviation 5. Let's see another way to do that. I can use a library called Mosaic. Again, if you don't have this library, this package or library in R, you can install it. Okay, if you don't have it, what you do is you do install.packages. Okay, and you type the name of the library. Okay, like, okay, you type the name of the library. Okay, and this will install the package. And once this is done, so you run your set of code, and when this is done, you can actually comment it out because you don't want to redo that several times. Then you load the library, with the keyword library mosaic, and then you can try the function xpnorm. So let's try that. So xpnorm of 2 will actually display, okay, it will graphically display the normal, standard normal, because I'm not providing the mean and the standard deviation, and we'll plot the value 2 here, which I'm actually entering as input, and will give you the probabilities. Probability that x is less than 2, and probability that x is more than 2. Okay, so I can do, okay, the same as before, and you can see how I can get my probability here. Okay, in the middle, my probability is this. Okay, so I get exactly the same value here as I did before by hand. Okay, remember the value, I got this value here. Okay, I calculated this value here. Okay, so you can do that without graphic here and here, and what I'm doing here, I'm doing that graphically here. Okay, I'm showing you the probabilities. In fact, they are here also. Okay, actually, not all probabilities are calculated, but you can see them here. So the probability of the 3 zones are here. Okay, and by colors. Okay. All right, quantiles, you can do, this is the opposite now. Instead of using xp norm, you can use xq norm, and xq norm will calculate where to cut the distribution to have a certain probability. So here I have a standard normal distribution, okay, because mean equals 0 and standard deviation is 1, and I'm asking what is a cut point that cuts an area of 30% or probability 0.3 to the left of this cut point, and the answer is this. Okay, so if I want to cut an area of 5%, just 5%, this cut point will move toward the left. Okay, so now I have 5% here, 90% probability there. Okay. If I want, on the other hand, if I want 95% probability, I will move up, okay, to the right, and this here I have 5% here and 95% here. So I need to take 1.64, okay, to get the probability that a normal distribution is greater than 1.64 is 5%. Okay. Okay, I said that I would show you an animation of the law of large number. Okay, so here we are. What I do is I use the package animation. I use a save GIF function. Okay, and I will create an animation where for I do I do a loop of 1,000 attempts, and each attempt what I do is I simulate a binomial of size 10 essentially, and I count how many times I see the number 2. Okay, so this is I'm using the sample function that I've explained in M2L2, and I count how many times I see 2, and I record that in my counter here. This is my counter. Okay, and for every even iteration, okay, every even iteration, I actually plot my observed counts and my theoretical counts. Okay, so if I do that, let me do that, show you that. So this takes a little bit of time, okay, and this will save a file that here I've named demo.gif on my computer. Okay, so I would generate in fact 500 images. I'm doing 1,000 iteration, and every even iteration I do a plot. Okay, so this will generate actually 500 images. Okay, that would be assembled as an animated GIF on my computer. Okay, and you are going to see automatically. You are going to see the browser will open, and you will see the animation. Okay, when it's finished. Okay. So how do I know if it's finished or not? You can look at the green bar here. As long as the green bar is running, okay. So here we are. Okay, we have this animation. The blue points are the data, simulated data, and the green point are the theory. Okay. So here I'm actually checking if the strong law of large number holds, meaning that my empirical frequencies, blue points, should converge to my theoretical frequencies, green points. Okay, so eventually the blue should be behind a green. Okay, or the green should be in front of a blue. Okay, eventually. Here I have done 500 steps or close to 500 steps. I'm doing a total of 1,000 steps. Okay, you see that those have already converged. Okay, but these are more difficult. Okay, I need more trials to converge with those. Okay, so let's see what happens here. 600. Okay, so I mean it may take a lot of attempts, okay, to converge. Okay, we are getting close. You see here now these two here are now very close, getting very close to their values. Okay, and the value of 0 is the most difficult. Well, it's because there's more variation in that value. Okay, and of course there are fluctuations. Okay, and of course you would see this blue and green collapse to to each other, and this cycle is done. Okay, so here we are, and now we have this. I can include that in my. Okay, I can include that in my. I can use knit include graphics. Okay, to include my GIF file in my RNB file. Okay. Finally, let me show you. Okay, the final example. Okay, let me close this series of exercises by some remark on Markov chains. Okay, Markov chains. So here, well, I wanted to put an image of Markov. Well, So let's say I have a set of symbols, okay, here, R, S, C, 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 okay. And what I want to do is I want to look at how many times R is followed by R, or R is followed by C, or R is followed by S, or C is followed by R. So I'm looking at what are called 2-grams, okay? 2-grams, so sequences of two symbols and their of two consecutive symbols. So the only sets of two consecutive symbols, I have three symbols, I have all these possibilities. Okay, I can arrange them as the first symbol here, the second symbol there, and I can actually, well, I can show you, okay, I can show you what I get. I get this, okay. R is never followed by R. R is followed by C 3 times. R is followed by S 1 time. Okay, and you can check that, okay. R followed by R, never, but R followed by C here, R followed by C here, okay, R followed by C here, and R followed by C here, so 3 times, okay. So you can easily get this matrix here, okay. You can get this matrix here, you can put your numbers here, okay, and you get this matrix here. Now what you can do is you can divide each row of this matrix by the sum of the numbers. So the sum is 4 here, the sum here is 11, and the sum here is 4. Okay, so I divide the first row by 4, the second row by 11, and the third row by 4. So I divide row number 1 by the sum of row number 1, row number 2 by the sum of row number 2, and row number 3 by the sum of row number 3. And I get, if I do that, if I normalize the rows of my matrix, I get what is called a transition matrix, Markov transition matrix. So basically, this tells me, okay, that the probability that if I have an R, the next letter will be a C is 0.75%. So you can now use, okay, this transition matrix to generate an artificial sequence from which looks like this one, which respect the same type of frequencies, okay? And that's basically the idea behind Markov chains. So instead of actually doing that operation by hand, as I did, as an application of what I showed in module 2, okay, you can also normalize like this. You can use apply, okay, and you can you can design a function to normalize by dividing by the sum. And if you do that and you need to transpose the result, you'll get the same result. Okay, so let me show you that. So you can see that this matrix here, computed by manual normalization, okay, dividing by this by sums by hand if you want. Well, here we do something smarter, okay, and more general. That's it for this video. I hope that you liked it, okay, and I will post it on Brightspace.